What if one of the most devoted systems in your life has been working for you every moment, and you have never truly noticed it? Right now, beneath your skin, across the quiet landscape of your blood and tissues, trillions of microscopic guardians are moving in slow, coordinated patterns, recognizing, remembering, protecting. They do not ask for your attention. They do not wait for instruction. They simply continue, shaped by ancient biology and quiet intelligence, sustaining you in ways that are almost impossible to see. This is your immune system, not a single organ, but a living network spread through your entire body, always present, always listening. Tonight, we will move gently through this hidden world, one calm fact at a time. Not to memorize, not to analyze, but simply to notice. To follow these quiet processes as they unfold beneath the surface and let their steady rhythm carry you softly toward rest. Your immune system is home to approximately 2 trillion immune cells, a number so large it feels more like weather than biology, more like a tide than a count. These 2 trillion cells make up roughly 3% of your body's total cell population, which itself numbers somewhere between 30 and 37 trillion living units, each one performing its quiet role without your instruction or awareness. To hold that number gently in your mind for a moment, 37 trillion cells, and within that vast constellation, 2 trillion devoted entirely to your protection. They do not sleep. They do not rest. They circulate through your blood and nestle into your tissues, patrolling borders you will never see, keeping vigil in a darkness that is also somehow full of light. You do not have to ask them to work. You do not have to remember to breathe life into them. They simply are, present, watchful, and endlessly faithful to the body they call home. Somewhere in the soft interior of your body, there exists something like an infinite library. A collection of molecular shapes so vast that scientists can only gesture at its edges. Through a process called VDJ recombination, your immune system shuffles and rearranges segments of genetic code the way a musician might rearrange the notes of a scale, and from that shuffling comes the capacity to generate over 1 trillion unique antibody types. Some estimates reach far beyond even that, into numbers that have no comfortable name. Quintillions, some say, a word that dissolves before it can be fully imagined. Each antibody is a key shaped for a single lock, a recognition so precise that it can reach into a crowd of billions and find the one molecule it was made to meet. Your body carries this library not as a burden, but as a birthright, written into you before your first breath. If you were to take a single teaspoon of your blood, just 5 milliliters, a measure so small it would barely fill a thimble, and look at it under a lens powerful enough to reveal its hidden world, you would find between 5 and 10 million white blood cells drifting there, each one a soldier of a different kind, each shaped by years of evolution to recognize danger in its many forms. 5 to 10 million in a teaspoon. Your body holds approximately 5 liters of blood in total, and so the arithmetic begins to shimmer into something almost incomprehensible. Billions upon billions of white cells moving through you right now, even as your breathing slows and your muscles soften towards sleep. You are not empty in the dark. You are abundantly, remarkably full. Unlike the heart, which beats in one place, or the brain, which rests in its cradle of bone, the immune system has no single address. It is everywhere and nowhere, distributed across the whole geography of you, threaded through your blood, tucked into the soft tissue of your lymph nodes, nestled deep in the spongy chambers of your bone marrow, curled inside the spleen, woven into the lining of your gut, and spread across the vast landscape of your skin. It is less like an organ and more like a weather system, present in every altitude, responsive to every shift, moving through you the way wind moves through a forest, invisibly, constantly shaping things you cannot see. Because it has no single home, it cannot be lost in one wound, silenced in one place. It is, in the truest sense, everywhere you are. Deep inside the hollow of your bones, in the soft red marrow that lives there like something warm and tidal, your body performs one of its most astonishing daily acts. It manufactures approximately 500 billion blood cells every single day. 500 billion before breakfast, before the first word spoken, before even the first conscious thought of morning. Many of these cells are red, carrying oxygen the way a river carries light, but woven among them are the white cells, the immune architects, the cells that will become the defenders and the memory keepers and the quiet diplomats of your inner world. They are born in darkness, in the marrow, where no light reaches and no sound travels, and yet they emerge into your bloodstream already knowing, already oriented, already leaning toward their purpose. Birth and duty arriving in the same breath. Distributed across the landscape of your body like a network of small, listening outposts, there are between 600 and 700 lymph nodes, tiny bean-shaped structures tucked beneath your arms, along your neck, in the hollows of your groin, deep within your chest and abdomen, quietly monitoring the fluid that moves between your cells. This fluid, called lymph, carries with it the debris of daily life. Fragments of dead cells, wandering bacteria, the occasional virus that has wandered too far from its intended course. The lymph nodes filter all of it, the way a quiet pond might filter the rain that falls into it, and when they detect something that does not belong, they swell gently with the effort of response, which is why, when you are unwell, a careful hand pressed to your neck can feel them working, warm and present, doing what they have always done. Your spleen, a fist-sized organ tucked quietly beneath your left rib cage, is among the most industrious filters in all of nature. Every minute, approximately 150 milliliters of blood pass through its soft chambers, which means that in a single hour, the spleen processes roughly 9 liters of blood, more than your body's entire blood volume, cycled through and returned, cleansed and renewed. It removes aging red blood cells the way a careful gardener removes spent blossoms, making room for the new. It captures bacteria and fragments of cellular debris. It holds a reservoir of blood platelets ready to be released in moments of need. And it does all of this without a word, without complaint in the wordless dark of your interior. Every hour, every night, every quiet moment you have ever lived. The immune system does not work in silence. It speaks, not in words, but in the language of chemistry, through more than 100 different signaling proteins called cytokines. These molecules are the immune system's postal network, its telegraph, its whispered chain of messages passed from cell to cell across the vast interior distances of the body. Some cytokines say, "Come here, there is danger." Others say, "Stand down, the threat has passed." Still others say, "Remember this, hold the shape of this invader in your memory because we may meet it again." They rise and fall like tides, like bird song at dusk, like the shifting harmonics of a chord that never quite resolves, always in motion, always speaking, always keeping the vast community of your immune system in its living, breathing conversation. Before any pathogen reaches your blood, before any immune cell stirs into action, there is your skin, the body's first and most expansive line of protection, stretching across approximately 2 square meters of your surface, holding you together the way a river holds its banks. It is not merely a covering, it is an active immune organ populated with specialized cells called Langerhans cells that drift through its layers like gentle sentinels, sampling the environment, detecting what should not be there, sending quiet signals inward when the border has been breached. Sweat and oils on your skin create a chemical environment too acidic for many bacteria to survive. Even the simple act of skin cells shedding 20 to 40,000 dead cells every hour carries away whatever may have landed there. You are, in a sense, always renewing your first and oldest protection. Perhaps the most surprising fact about the immune system is where so much of it lives, in your gut. Lining the long, winding interior of your digestive tract is nearly 70% of the body's entire immune tissue, a vast, warm, intricate network called the gut-associated lymphoid tissue, or GALT, that monitors every molecule you swallow, every fragment of food, every bacterium that makes the journey through your interior world. It is no accident that this is so. The gut is the place where the outside world most directly enters your inside one, where the boundary between self and not self is thinnest, most permeable, most in need of careful watching. And so the immune system, in its ancient wisdom, has placed its greatest concentration of sentinels exactly there, at the threshold, in the warm and living dark. They are called leukocytes, from the Greek for whitened cell, and they are the primary living force of your immune defense. Unlike red blood cells, which spend their lives in a single devoted purpose, leukocytes are shapeshifters and specialists, a community of different kinds and callings, each evolved to play a distinct role in the protection of the whole. Some are first responders, arriving at a wound before the inflammation has even fully begun. Others are slower, more deliberate. They arrive later, armed with a more refined understanding of the specific threat. Some remember, some coordinate, some simply consume, engulfing what does not belong the way a tide swallows a stone. Together, these white blood cells form a living society inside you, one that has been evolving its strategies for hundreds of millions of years, long before you, long before any version of the creature you came from ever drew its first breath. Among the leukocytes, there are 5 great families, each with its own temperament and purpose. The neutrophils, swift and numerous and first to arrive. The eosinophils, patient specialists who rise to meet parasites and the particular agitations of allergy. The basophils, rare as certain birds, their role still partly mysterious even to science. The lymphocytes, the brilliant architects of memory and targeted response. And the monocytes, the travelers who leave the bloodstream entirely, entering tissues to become something new. These 5 families do not compete. They coordinate, each one filling a role that the others cannot, each one part of a system so elegantly balanced that, for most of your life, you will never consciously feel it working. They simply tend to you, the way seasons tend to a landscape, differently in every moment and always in service of the whole. Of all the white blood cells circulating through your blood at this very moment, between 55 and 70% of them are neutrophils, the most abundant, the most eager, the first to receive the alarm and move toward it. They are not subtle, they are not precise in the way that later immune responses will be. They are rapid and numerous and fierce in their willingness to sacrifice themselves, and that is exactly what the moment of first infection requires. Not elegance, but urgency. Not precision, but speed. A neutrophil recognizes the chemical signals of a wound or an intrusion the way a bird recognizes the sound of its own name, and it turns toward the source without hesitation, pushing through vessel walls and swimming through tissue fluid until it reaches the place where it is needed. It is perhaps the most faithful first responder in all of biology. The speed of the neutrophil's response is one of the quiet miracles of your body. When a pathogen breaches your defenses, when a cut opens in your skin or a virus slips past the mucosal lining of your throat, the injured cells release a cascade of chemical distress signals, and within just 30 minutes, neutrophils can detect those signals and arrive at the site of threat. 30 minutes. In the scale of biological time, this is nearly instantaneous. A first response as swift as a reflex, as immediate as flinching from heat. And they do not arrive alone. They come in waves, each wave reading the chemical trail left by the ones before, converging on the site of need in a coordinated rush that, to any invading microorganism, must feel something like a tide that only rises and never retreats. Among the immune system's most ancient strategies is one called phagocytosis, a word that comes from the Greek for to eat and cell, and describes exactly what it sounds like. The ability of certain immune cells to engulf and consume pathogens whole. The macrophage is the great practitioner of this art. It extends part of its membrane outward, flowing around a bacterium or a fragment of debris the way water flows around a stone until the invader is enclosed completely in a membrane bubble. And then, inside that bubble, it releases chemical agents that break the pathogen down, dissolving it into harmless components. Phagocytosis is among the oldest immune strategies on Earth, found in organisms far simpler and far older than anything with a spine. It is the body's original act of protection. Reach, enclose, dissolve. A gesture so fundamental it feels almost tender. A macrophage, whose name means big eater in Greek, can consume up to 100 bacteria before it exhausts the last of its capacity and dies. 100 separate acts of engulfing and destruction, each one requiring energy and chemical precision before the cell finally reaches the limit of what it can carry and gives itself entirely to the effort. There is something in this that moves quietly toward the poetic. A single cell, no larger than a grain of sand, facing 100 enemies and meeting each one at a time until it can meet no more. And then it becomes, in its death, part of what you know as pus, that pale accumulation of fallen immune cells that marks the site of a hard-fought battle. Even in ending, the macrophage leaves a record of its faithfulness. There is a class of immune cell called the natural killer cell, the NK cell. and its name is almost disarmingly direct for something that operates with such quiet efficiency. Natural killer cells patrol your body continuously, moving through blood and tissue in an endless circuit, and what sets them apart from most other immune cells is this: they do not need to be told what to recognize. They do not require a specific antigen presentation or a formal introduction to the threat. They are born already knowing how to identify cells that have been corrupted, cells infected by viruses, or cells that have begun the slow unraveling into cancer. And when they find such a cell, they bind to it and deliver a chemical instruction that causes the corrupted cell to dissolve from within. They are, in the truest sense, the immune system's quiet, ceaseless night watch. Eosinophils are not the most numerous of the white blood cells, nor the fastest, nor the most dramatic in their methods, but they are specialists of a particular and important kind. Their primary calling is the defense against parasites, the worms and larger organisms that are too big to simply be engulfed, too complex for the simpler strategies of the first responders. Eosinophils respond to these threats by releasing toxic proteins from their internal granules, a kind of chemical siege directed at an organism that cannot be swallowed whole. They are also deeply involved in allergic responses, which is why their numbers rise in the blood of people with asthma or hay fever, the body deploying them against a misidentified threat, the immune system's earnestness working, in this case, just a little too hard. Of all the white blood cells that travel through your blood, the basophil is the rarest, making up less than 1% of the total circulating leukocyte population. In a blood sample taken from a healthy person, you might find only a handful of them, drifting among millions of other cells like a word spoken very softly at the edge of a great conversation. Their relative scarcity has made them difficult to study, and even now, science does not fully understand every dimension of their role. What is known is that they are involved in allergic and inflammatory responses, that they release histamine and other chemical mediators, and that they carry a kind of quiet importance disproportionate to their numbers. The rarest voice in the chorus, and yet part of the harmony indispensably and irreplaceably. Monocytes are born in the bone marrow, released into the bloodstream, and for a time they simply circulate, patrolling, monitoring, waiting for a signal. And then, in response to certain conditions, they do something remarkable. They leave the bloodstream entirely, squeezing between the cells of blood vessel walls and entering the surrounding tissues. And there, in that new environment, they transform. A monocyte that enters tissue can become a macrophage, the great engulfer, the long-lived protector of that tissue. Or it can become a dendritic cell, the immune system's messenger and teacher. The monocyte does not arrive at its destination already knowing what it will be. It becomes what the tissue needs, shaped by context rather than fixed by fate. There is something in this that feels almost hopeful, a cell whose identity is not determined until it arrives at the place where it is needed. Dendritic cells are the immune system's messengers, its artists in a way, because what they carry is not a weapon but an image. When a dendritic cell encounters a pathogen, it does not simply destroy it. It processes it, extracting from the invader something like a molecular portrait, a fragment of its surface, a piece of its unique chemical signature, which is then displayed on the dendritic cell's own surface like a wanted poster. And then the dendritic cell travels to the lymph nodes, to the spleen, to wherever the other immune cells wait, and it presents that portrait to the lymphocytes, to the T cells and the B cells, training them to recognize this specific threat. Without the dendritic cell, the adaptive immune system would be brilliant and utterly blind. With it, the system can learn the face of any enemy it has ever met. Imagine being able to step directly through a wall, not breaking it, not tearing it, but flowing through it as though it were not quite solid, as though you and the wall were made of compatible things. This is, in essence, what white blood cells do through a process called diapedesis, the ability to squeeze through the junctions between the cells that line blood vessel walls, passing from the interior of the bloodstream into the surrounding tissue where a threat has been detected. The vessel walls do not break. The white cell does not force its way through. Instead, the vessel cells respond to chemical signals from the immune cell and from the site of inflammation, loosening their connections briefly to allow passage. It is one of the body's most elegant negotiations. A door that opens when the right knock comes and closes gently after. An antibody is shaped like the letter Y, a forked, elegant molecule whose two raised arms are designed to bind to one specific target and no other. That target is called an antigen, a fragment of a pathogen's surface, a molecular signature as unique as a fingerprint that the immune system learns to recognize and remember. The antibody binds to its antigen the way a key fits a lock, not by force but by fit, by the precise complementarity of shape meeting shape at the molecular level. Once bound, the antibody marks the invader for destruction, or neutralizes it directly, or recruits other immune cells to finish the work. It is a system of recognition so precise that it staggers the imagination, and yet it operates continuously throughout every hour of your life in the liquid world beneath your skin. Through a process called VDJ recombination, a kind of biological shuffling of genetic segments, like cutting and redealing an infinite deck of cards, the human immune system can theoretically generate more than 1 trillion unique antibody structures. Some researchers believe the potential library reaches far beyond even this, into numbers that cannot be practically spoken, quintillions of possible molecular shapes, each one a potential key to a lock that may or may not exist in nature. Your body does not produce all of these at once, of course. The living immune system is not a library of quintillions, but rather a continuously curated collection, always making new entries based on what the world presents. But the potential is there, written into your genome, waiting for the moment when any particular key is called upon to be made. The first time your immune system encounters a completely new pathogen, something it has never seen, never catalogued, never prepared for, it does not respond instantly with targeted antibodies. It takes time. The B cells must recognize the threat, receive instruction from helper T cells, multiply, and then differentiate into plasma cells that can produce the specific antibody needed. This process takes approximately 10 to 14 days, a span of time that, in the early history of infectious disease, was often the most dangerous interval a person ever crossed. During those days, the innate immune system holds the line as best it can, the neutrophils and macrophages working without the precision of antibodies, buying time for the adaptive system to forge its more elegant response. The 10 to 14 days of first encounter is the immune system's most vulnerable and most heroic window. B cells are named for the bone marrow where they are born and matured, and their singular purpose, the one gift they are made to give, is the production and secretion of antibodies. Each B cell, upon activation, begins to multiply into a clone of identical cells called plasma cells, each one dedicated to producing a single kind of antibody at a rate of thousands of molecules per second. Thousands per second from a single cell, and in the midst of an immune response, there may be millions of such plasma cells all producing simultaneously, flooding the blood with the targeted molecular keys needed to identify and neutralize the invader. The B cell does not produce antibodies for every possible threat simultaneously. It waits until it is needed, and then it gives everything it has. Among all the remarkable features of the immune system, one of the most quietly astonishing is the exquisite specialization of each individual B cell. Every B cell produces only one type of antibody, not several, not a range. One, a single molecular shape designed to fit a single antigen and no other. This is not a limitation, it is a feature of a system designed for precision rather than generality. The diversity of the immune response comes not from any single cell's versatility, but from the vast population of different B cells, each one tuned to a different frequency, together spanning a range of recognition so wide it touches the edges of the possible. It is like an orchestra where each instrument plays only one note, and the music comes not from any single voice, but from all of them, playing together. After an infection is resolved, after the antibodies have done their work and the pathogen has been cleared and the inflammation has subsided and the body has returned to its ordinary quiet, something remains. Some of the B cells that were activated during the response do not die with the plasma cells. Instead, they transform into memory B cells, long-lived sentinels that carry the molecular record of the defeated invader and persist in the body for years, for decades, sometimes for the remainder of a human lifetime. They are the immune system's archive, its long memory, its way of ensuring that the body never truly forgets what it has already learned to overcome. Should the same pathogen return, these memory cells can respond in hours rather than weeks, a recognition as swift and certain as remembering a face you have not seen in years. If the B cells are the immune system's antibody factories, then the T cells are its commanders, the cells that orchestrate, direct, and give meaning to the entire adaptive immune response. They are born, like all immune cells, in the bone marrow, but their maturation takes place in a different organ entirely, the thymus, a small gland that sits just above the heart and whose name gives the T cell its letter. In the thymus, T cells undergo a rigorous education. They are tested for the ability to recognize the body's own cells as self, and any T cell that fails this test, that might turn against the body's own tissue, is eliminated before it can cause harm. Only the cells that pass emerge into the bloodstream, ready for their role in the grand conversation of immune defense. The thymus is, in this sense, the immune system's school, and the T cell is its most carefully graduated student. Among the T cells, there is one type whose name describes its calling with unusual precision, the helper T cell. It does not kill, it does not engulf, it does not produce antibodies. What it does is signal. It releases a cascade of chemical messengers called cytokines that activate B cells to produce antibodies, that wake the cytotoxic T cells into action, that amplify and coordinate the entire adaptive immune response. Without the helper T cell, the other cells of the adaptive system would be like musicians who have arrived at a concert hall with no conductor, present, capable, but uncertain how to begin. The helper T cell is the one that raises its hands, that sets the tempo, that tells each section when to enter and how loud to play. It is perhaps the most quietly essential cell in the entire immune system. There is a kind of immune cell called the cytotoxic T cell, the killer T cell, and its method is one of the immune system's most remarkable and merciful inventions. When a cytotoxic T cell identifies a cell that has been infected by a virus, or a cell that has begun its slow mutation toward cancer, it does not destroy the cell from outside. Instead, it binds to it and injects it with proteins, perforins, and granzymes that trigger a process called apoptosis, a programmed, orderly self-dissolution in which the infected cell breaks itself into neat fragments that can be safely consumed and cleared. The cell does not burst, does not release its contents in a way that might damage surrounding tissue. It simply ends, cleanly and completely, like a note that resolves rather than breaks. The cytotoxic T cell offers its targets the gift of an organized ending. Every system of great power requires a counterbalance, something that knows when to stop, when to quiet the response that has done its work, and must now stand down. In the immune system, this role belongs to the regulatory T cell, sometimes called the Treg, a cell whose purpose is not to attack but to restrain, not to amplify but to quiet. Once an infection has been cleared and the acute phase of the immune response is complete, regulatory T cells release suppressive signals that tell the immune system to reduce its activity, to allow inflammation to subside, to return the interior landscape to its ordinary calm. Without them, the immune system would continue to attack long after the threat was gone, as indeed happens in some autoimmune conditions. The Treg is the immune system's sense of proportion, its understanding that force must always know when it is no longer needed. Over the course of a human life, the adaptive immune system builds a record, a kind of molecular autobiography of every pathogen it has ever encountered and defeated. The memory cells that form after each immune response are added to this archive, and the archive grows, expanding across decades, each entry representing not a wound but a lesson, not a defeat but a victory stored so that it need not be won again. Scientists believe the adaptive immune system can maintain the memory of billions of different pathogens simultaneously. A library of encounters so vast that it constitutes, in some sense, the immunological history of a person's entire life. Every illness you survived as a child, every infection that passed through you and left, every battle fought quietly in the night while you slept, all of it held inside you, patient and precise and enduring. Inflammation has a poor reputation. It is often spoken of as something to be suppressed, something gone wrong, something the body is doing against itself. But inflammation, in its original and proper form, is not a malfunction. It is a deliberate, coordinated, purposeful signal, the body's way of saying, something has happened here, and we are responding. It is the first chapter of healing, not a symptom of failure. The redness and warmth and swelling of an inflamed cut are not signs that something is broken. They are signs that the immune system is working exactly as it was designed to, rushing resources to the site of injury, creating conditions hostile to invaders, beginning the long, careful work of repair. Inflammation, at its best, is the body's most honest announcement that it has noticed and that it cares. When tissue is damaged, when a thorn breaks the skin or a bacterium breaches a membrane, the cells of the injured area release a cascade of chemical signals that the immune system reads as an emergency call. Among the most important of these signals are histamine, released by mast cells, and basophils and prostaglandins, released by damaged cell membranes. Histamine causes nearby blood vessels to dilate and become more permeable, allowing immune cells to move out of the bloodstream and into the tissue. Prostaglandins amplify the sensation of pain, which is the body's way of communicating to the conscious mind. Protect this area. Give it rest. Do not use it carelessly while it heals. The alarm system of inflammation is ancient and eloquent, a chemical language spoken between cells that predates human language by hundreds of millions of years. When you press your fingers to a wound and feel its warmth, the particular heat of inflamed skin, what you are feeling is the immune system at work. The redness and warmth of inflammation occur because the blood vessels in the affected area dilate, widening to allow a greater volume of blood to flow through. More blood means more immune cells arriving at the site, more chemical mediators flooding the tissue, more resources marshaled for the work of repair and defense. The skin flushes. The area grows tender. These are not signs of the body failing. They are signs of the body attending, of the immune system turning its full attention toward a single point, the way sunlight concentrates through a lens. The warmth is, in its way, a form of care made physical, made visible, made warm enough to feel beneath your hand. A fever feels like a punishment, the burning heaviness of it, the way it wraps around you and makes even the cool of a pillow feel brief and insufficient. But the fever is not the illness. The fever is the body's ancient and carefully designed response to illness, one of the immune system's most powerful and intentional tools. Elevated body temperature, even a degree or two above normal, creates conditions deeply hostile to bacterial replication. Many pathogens are optimized for the normal temperature of the human body, and when that temperature rises, their ability to reproduce slows, their enzymes destabilize, their advantage narrows. At the same time, the fever speeds the activity of immune cells, quickens their patrol, sharpens their response. The fever is the body running hot on purpose, doing what it has always known how to do. The decision to raise the body's temperature does not happen in the bloodstream alone. It requires a conversation between the immune system and the brain, specifically with a small but enormously important structure called the hypothalamus, which sits at the base of the brain and serves as the body's master thermostat. When immune cells detect a pathogen and release signaling molecules called pyrogens, those signals eventually reach the hypothalamus, which responds by resetting the body's temperature target upward. The shivering that comes with the onset of a fever is the body's method of generating heat quickly, raising the temperature to match the hypothalamus's new instruction. And when the fever breaks, that sudden flooding relief, that return to coolness, it is the hypothalamus resetting once more, the brain signaling that the emergency has passed. The precision of the immune system is such that even a change of a single degree Celsius in body temperature, a shift so subtle that many people would not consciously feel it, can measurably increase the efficiency of immune cell activity. 1 degree. In a system built on the most delicate chemical interactions, the difference between 37 and 38 degrees Celsius is not trivial. It is the difference between enzymes operating at their standard pace and enzymes running with a slight but meaningful urgency, between immune cells moving at their ordinary speed and immune cells quickened into a pace that might shorten the duration of an illness by a day or two or more. The body understands temperature as a tool, as a lever, as a way of tilting the conditions of the interior world slightly and consequentially in favor of its own survival. Pus, that pale, thick fluid that sometimes appears at the site of an infection, has a reputation that does not honor what it actually represents. It is not waste or failure or a sign of corruption. It is, almost entirely, a memorial. Pus is composed predominantly of dead and dying neutrophils, the first responder immune cells that arrived at the site of infection and gave themselves entirely to the containment of the threat, consuming bacteria until they could consume no more, releasing toxic chemicals into the battle zone, sacrificing their own cellular integrity so that the infection would not spread. What collects in a wound is the record of their effort, the accumulated bodies of cells that went first and held the line until the rest of the immune system could arrive. Pus is, in the truest sense, a monument to the faithful dead. One of the immune system's most elegant strategies is something called apoptosis, programmed cell death, or in its Greek original, a falling away, like leaves from a tree. When an immune cell identifies a cell that has been irreparably infected by a virus or has begun the dangerous process of becoming cancerous, it delivers a signal that causes the compromised cell to disassemble itself in an orderly, controlled manner, shrinking, fragmenting its DNA, packaging its contents into small, neat parcels that can be safely consumed and cleared by macrophages without spilling their contents into the surrounding tissue. Apoptosis leaves no mess, it leaves no trigger for further inflammation. It is the immune system's way of ending a threat not with violence but with precision, a dissolution so controlled it might almost be called peaceful. Inflammation, like fire, is invaluable when it is brief and purposeful, and dangerous when it smolders without resolution. Chronic, low-level inflammation, the kind that does not rise in response to a specific infection but instead persists quietly in the background of the body year after year, has been linked by researchers to a range of serious conditions: heart disease, type 2 diabetes, depression, cognitive decline, and certain cancers. This kind of inflammation does not announce itself the way an acute infection does. It is not dramatic. It is quiet and slow and cumulative, like water finding the weak places in a stone wall over many winters. Understanding it and learning what keeps it burning, poor sleep, chronic stress, certain dietary patterns, smoking, is one of the central concerns of modern medicine. Of all the things you can do for your immune system, the one that requires the least effort and offers among the most profound returns is also the most ordinary: sleep. During deep sleep, the body enters a state of active immune maintenance. Cytokines are released that promote tissue repair and the consolidation of immune memory. Inflammation is gently modulated, the cells damaged by the work of the day are quietly cleared. Sleep is not a passive state. It is the immune system's most productive shift, the hours when it does its deepest housekeeping, its longest range planning, its most careful tending. Every hour of rest you give yourself tonight is not time away from living. It is time your immune system uses to make sure that the living continues, healthy and sustained, into all the days still ahead of you. One of the most profound gifts of the adaptive immune system, the feature that separates it from all the more ancient and general defenses of the body, is its memory. Immunological memory is the capacity to remember a pathogen that has been encountered before and to respond to it upon re-exposure, not with the slow, uncertain process of a first encounter, but with the swift and decisive authority of long familiarity. Where a first immune response might take 10 to 14 days to mount effectively, a memory response can begin within hours. The immune cells already primed, the antibodies already partially templated, the whole machinery oriented and ready before the invader has had time to establish itself. It is the difference between learning a language for the first time and speaking one you have known since childhood. The words come faster when you have spoken them before. Memory B cells and memory T cells, the long-lived keepers of immunological experience, have been documented to survive in the human body for 75 years or longer. 75 years. Nearly an entire human life carried in a cell no larger than a grain of salt, holding the molecular portrait of a pathogen that the body encountered once, perhaps in childhood, and has never needed to fear again. Scientists studying survivors of the 1918 influenza pandemic discovered nearly 90 years later that some still carried memory cells bearing antibodies to that specific strain of virus, a cellular memory outlasting careers, children, grandchildren, almost outlasting the memory of the pandemic itself. The immune system is, in this sense, the body's longest and most faithful archivist. A vaccine is, at its most fundamental level, a lesson delivered without the cost of illness, a way of introducing the immune system to a pathogen or to a fragment of a pathogen in a form that allows the immune system to learn from the encounter without being harmed by it. Vaccines may contain weakened or inactivated forms of a pathogen or specific proteins from a pathogen's surface, or, in the case of more recent technologies, genetic instructions that prompt the body's own cells to produce an antigen the immune system can learn to recognize. In each case, the result is the same. Memory cells form, antibodies are templated, and the adaptive immune system files away the information it will need to respond swiftly and decisively if it ever meets the real thing. The vaccine does not protect in the moment it is given, it plants a memory that protects for years or decades or a lifetime. History often credits Edward Jenner with creating the first vaccine. His 1796 discovery that infection with the mild cowpox virus conferred protection against the deadly smallpox stands as one of the great turning points in the history of medicine, and Jenner's contribution is real and remarkable. But long before Jenner's careful observations in the English countryside, the practice of variolation was already ancient in parts of China, India, and sub-Saharan Africa. Variolation involved deliberately introducing small amounts of material from a mild smallpox lesion into a healthy person, a risky but often effective practice that had been refined across generations, transmitted through healers and mothers and community knowledge, centuries before European science gave it a name. The vaccine was born not once but many times in many places, by many kinds of knowing. Smallpox was, for most of human history, one of the most terrifying forces on Earth, a disease that killed approximately 30% of those it infected and left survivors bearing its marks for the rest of their lives. And then, through one of the most remarkable coordinated efforts in the history of medicine, a global vaccination campaign led by the World Health Organization, spanning decades and crossing every border and ideology of the 20th century, it was gone. In 1980, the WHO officially declared smallpox eradicated, the first and, as of now, the only human infectious disease ever to have been completely eliminated from the earth by human action. The virus does not exist in nature anymore. It lives only in 2 laboratory freezers, one in the United States, one in Russia, the last remnants of something that once threatened all of humanity. Not all vaccines confer the same duration of immunity, and this is not a failure of the vaccine. It is a reflection of the nature of the pathogen it targets. Some vaccines, like the one for measles, stimulate such a durable immune memory that a single childhood vaccination may provide protection for the rest of a person's life. Others, like the annual influenza vaccine, must be reformulated and administered every year, not because the memory fades, but because the virus itself mutates so rapidly that last year's memory no longer fits this year's threat. The influenza virus shifts its surface proteins continuously, shuffling the very antigens that the immune system learned to recognize, presenting a new molecular face each season. The annual flu vaccine is, in this sense, not a repetition, but a new lesson. The immune system's continuing education in a subject that keeps rewriting its own textbook. Herd immunity is a concept as quietly beautiful as it is practically powerful. When a sufficient proportion of a population has become immune to a disease, through prior infection or through vaccination, the pathogen can no longer find enough susceptible hosts to maintain its chain of transmission, and it begins to retreat. The disease cannot spread efficiently. It finds dead ends everywhere it turns. And in this retreat, the pathogen becomes unable to reach the people who cannot be vaccinated, the newborns too young for certain vaccines, the immunocompromised patients whose immune systems cannot mount a full response, the people for whom a vaccine did not produce sufficient antibodies. Herd immunity is, in its deepest sense, a collective gift, the protection of the many offered to the most vulnerable among them through no action of their own. For a disease as contagious as measles, a virus so easily transmitted that a single infected person can spread it to 12 to 18 others in an unprotected population, preventing outbreaks requires a very high level of community immunity. Scientists estimate that measles requires approximately 95% of a population to be immune before herd immunity becomes effective. 95 out of every 100 people protected, so that the 5 who are not cannot be reached by the virus's invisible transit from breath to breath, from touch to touch. When vaccination rates fall below this threshold, when the proportion of protected people drops even a few percent, the virus finds its openings and outbreaks follow. 95% is not an arbitrary number. It is the precise mathematics of protection, the exact proportion at which a community becomes a shield. Before a newborn's own immune system has fully matured, before its lymphocytes have been educated and its memory cells have accumulated any experience, it is already protected in part by a gift carried in its mother's milk. Breast milk contains antibodies, primarily of a class called immunoglobulin A, or IgA, which are secreted into the milk and swallowed by the infant with every feeding. These maternal antibodies line the surfaces of the infant's gut and respiratory tract, providing a passive immunity, borrowed protection carried from one immune system to another across the warm and intimate medium of nourishment. It is among the most ancient forms of immune transfer in mammals, a system evolved over millions of years, and it is still working today in this quiet and ordinary and extraordinary way. Every feeding, a small and complete act of protection. Your body is home to a community so vast and so diverse that it constitutes an ecosystem unto itself. Approximately 38 trillion microbial cells, bacteria, fungi, viruses, archaea, live in and on your body, a number roughly comparable to the total count of your own human cells, so that you are, in a very literal sense, as much microbe as you are human, a partnership between your genome and the genomes of trillions of other living things. The majority of these microorganisms live in your gut, concentrated especially in the large intestine, where they ferment dietary fiber, produce vitamins, regulate the pace of digestion, and engage in a continuous, complex conversation with the immune cells that line the gut wall. They are not passengers. They are collaborators, and your immune system has been shaped over millions of years of evolution to coexist with them, to tolerate the beneficial and to repel the harmful, to maintain a balance as intricate as any ecosystem on Earth. The immune system does not arrive fully formed at birth, knowing everything it will need to know. Much of its education happens in early life, through contact with the environment, and a crucial part of that education is provided by the microbiome. The trillions of bacteria that colonize the infant gut in the first weeks and months of life actively help calibrate the immune system, teaching it to distinguish between the microorganisms that belong, the commensals, the beneficial residents, and the pathogens that must be expelled. They do this through constant chemical signaling, through the presentation of microbial antigens to the gut immune tissue, through the production of metabolites that shape the behavior of immune cells. The microbiome is, in this sense, the immune system's earliest and most continuous teacher, present from the first days of life, shaping its student in ways that will echo for decades. One of the microbiome's most important roles is the regulation of immune balance, the calibration between inflammatory and anti-inflammatory responses that keeps the immune system effective without allowing it to tip into the chronic activation that causes harm. Certain gut bacteria produce short-chain fatty acids, particularly butyrate, that directly nourish the cells lining the colon and promote the development of regulatory T cells, the immune system's peacekeepers, the cells responsible for dampening inflammation once a threat has passed. When the microbiome is diverse and healthy, this balance is maintained with the ease of long practice. When it is disrupted by poor diet, antibiotics, chronic stress, the balance can shift, and the immune system may begin to lean toward a state of low-level activation, a smouldering readiness that serves no particular purpose and does a particular kind of quiet harm. There is a body of evidence, gathered across cultures and climates, in farm children and city children, in studies spanning decades, that children raised in environments with greater microbial exposure tend to develop immune systems that are more balanced, more tolerant, less prone to the overreactions we call allergy and autoimmunity. Children who grow up on farms, in close contact with soil and animals and the rich microbial diversity of the outdoor world, have measurably lower rates of asthma, hay fever and eczema than children raised in environments where such contact is limited. The immune system, it seems, needs to meet the world, needs to be challenged by the harmless and the benign in order to learn the difference between what must be fought and what can be tolerated. Exposure in early life is a form of education that no classroom can replicate. The hygiene hypothesis is the name given to a scientific observation that first emerged in the late 1980s and has since been supported by a growing body of research. that the dramatic rise in allergic and autoimmune diseases in industrialized nations over the past century may be related, at least in part, to the dramatic reduction in early life exposure to microorganisms. In societies where clean water, antibiotics, vaccines, and modern sanitation have eliminated or reduced many of the infections that once shaped the developing immune system, the immune system may be, in a sense, understimulated, trained too little by the harmless microbes that once taught it tolerance, and therefore more likely to find other targets for its attentions. The hypothesis is not an argument against cleanliness or vaccination. It is an argument for the complex and necessary relationship between the immune system and the living world it evolved alongside. Breast milk does more than deliver maternal antibodies. It also contains a specific kind of complex sugar called human milk oligosaccharides, compounds that the infant cannot digest, but that the infant's gut microbiome can, using them as food to establish and sustain the specific bacterial communities that will help calibrate the immune system in those first critical months. In this way, breast milk is not merely nourishment but a carefully composed ecological gift, a medium carrying not only the mother's own immune memory but also the substrates needed to cultivate the microbial community that will educate the infant's own immune system into being. It is a biological inheritance that runs deeper than genes, a mother's microbiome and immune experience transmitted across the intimate bridge of feeding, shaping a new immune system before it has had time to face the world on its own. Approximately 90% of the body's serotonin, a molecule most people associate with mood and well-being, is produced not in the brain but in the gut, by the enterochromaffin cells of the intestinal lining. This serotonin does not cross the blood-brain barrier and does not directly produce feelings of calm in the mind. Its primary role in the gut is regulatory. It manages the timing and rhythm of intestinal movement, helping coordinate the muscular contractions that move food through the digestive system. But the gut and the brain are connected by an intricate two-way communication system, the vagus nerve, among other pathways, through which the state of the gut is continuously communicated to the brain and the brain's state is communicated back. The microbiome participates in this conversation, influencing the signals that travel upward, contributing in ways that science is only beginning to map to the felt experience of being in a body. Antibiotics are among the most important and life-saving medicines ever developed. They have transformed the landscape of human illness, turning infections that once killed into conditions that resolve in days. But they carry a consequence that is worth understanding with gentleness and without alarm. They do not distinguish between the bacteria they are targeting and the bacteria that belong, and so in the course of eliminating a pathogen, they also reduce the diversity of the microbiome, sometimes significantly, sometimes for weeks or months after the course of treatment is complete. During this time, the reduced microbial diversity means a reduced calibration of the immune system, a temporary shift in the delicate balance that the microbiome helps maintain. The body restores itself gradually as the microbial community repopulates. Fermented foods, dietary fiber, and thyme are among the gentlest supports for that restoration. There are foods that the microbiome appears to welcome. Foods that increase the diversity of the microbial community and, through that diversity, modulate the immune system toward greater balance and resilience. Fermented foods in particular, yogurt, kefir, kimchi, sauerkraut, miso, and others that have been part of human diets for thousands of years, have been shown in clinical studies to increase the diversity of gut microbiome species and to reduce certain markers of immune activation. They introduce live microbial cultures into the gut, and they provide the microbial community with the substrates it needs to thrive. Eating them is, in a quiet and practical way, a form of tending, the same kind of tending a gardener offers to soil, adding what the living system needs to remain rich and varied and capable of sustaining itself through every season. In recent years, researchers have begun to speak of the gut-brain immune axis, a three-way communication system connecting the microbiome, the central nervous system, and the immune system in a continuous bidirectional conversation whose implications are still being discovered. The gut communicates with the brain through the vagus nerve, through hormones, through microbially produced compounds that enter the bloodstream and cross into neural tissue. The brain communicates with the immune system through hormones and neurotransmitters that influence immune cell behavior. The immune system communicates with both through cytokines that affect mood, cognition, and gut function simultaneously. These three systems, once studied in isolation, are beginning to be understood as aspects of a single integrated whole, a reminder that in the body, as in most things, everything is always in conversation with everything else. The immune system's greatest strength, its ability to distinguish between self and not self, between what belongs and what does not, is also, in certain conditions, the source of its greatest vulnerability. Autoimmune diseases occur when this recognition fails, when the immune system turns its considerable force against the body's own tissues, as though they were foreign invaders. The word auto means self, and autoimmunity is, in its most literal sense, the body in conflict with itself, immune cells attacking structures that they should recognize as home. This failure of self-recognition can arise from genetic predisposition, from environmental triggers, from disruptions in the regulatory systems that are supposed to keep the immune response within its appropriate bounds. It is not a moral failing. It is a complexity of a system so sophisticated that sometimes its very precision leads it astray. There are more than 80 recognized autoimmune diseases, ranging from relatively mild conditions affecting a specific tissue to systemic illnesses that can touch nearly every organ in the body simultaneously. In the United States alone, approximately 50 million people live with an autoimmune condition, a number comparable to those living with cancer and heart disease combined, and yet autoimmune disease receives a fraction of the research funding and public awareness of those conditions. The 80+ diseases share a mechanism, the immune system targeting self, but they differ enormously in their manifestations, their triggers, their progression, and their treatment. What unites them is the same essential paradox: the body's most devoted protector becoming, in a specific and bounded way, a source of the harm it was designed to prevent. One of the most consistent and least fully explained patterns in autoimmune disease is the significant difference in rates between women and men. Women are diagnosed with autoimmune conditions at nearly twice the rate of men, and in some specific diseases the disparity is even greater, with conditions like lupus and Hashimoto's thyroiditis affecting women at rates 8 to 10 times higher. Researchers have proposed several hypotheses: that sex hormones, particularly estrogen, may modulate immune activity in ways that increase susceptibility; that the X chromosome, of which women carry 2 copies, may carry immune-related genes that, when expressed in duplicate, increase the sensitivity of the immune response; that pregnancy, during which the immune system must accommodate a genetically distinct person within the same body, may leave lasting changes in immune function. The answer, most likely, involves all of these things at once. Rheumatoid arthritis is an autoimmune disease in which the immune system produces antibodies, called rheumatoid factor and anti-citrullinated protein antibodies, that target the synovial membrane, the delicate tissue lining the body's joints. This membrane exists to keep joints lubricated and moving smoothly, and when the immune system attacks it, the result is inflammation, pain, swelling, and, over time, the gradual erosion of cartilage and bone at the affected joints. Rheumatoid arthritis affects approximately 1.5 million Americans and can begin at any age, though it most commonly appears between the ages of 40 and 60. It is a systemic disease, meaning it affects the whole body, not only the joints, and people with rheumatoid arthritis have elevated risk of cardiovascular disease and other complications, a reminder that the immune system, wherever it turns its attention, shapes the health of everything around it. In type 1 diabetes, the immune system makes an error of identification that has lifelong consequences. It produces T cells and antibodies that target the beta cells of the pancreas, the specific cells, clustered in small groups called the islets of Langerhans, that produce insulin. As the immune system destroys these cells, the pancreas loses its ability to produce insulin, and the body loses its ability to regulate blood sugar in the way it was designed to. Unlike type 2 diabetes, which is associated with lifestyle and metabolic factors, type 1 is an autoimmune disease, not chosen, not caused by diet, not preventable by ordinary means. It can appear in childhood, sometimes very suddenly, and it requires lifelong management with insulin. The beta cells, once destroyed, do not regenerate. What the immune system unmakes in this disease, it cannot unmake undone. Multiple sclerosis is a disease of the nervous system driven by the immune system. a condition in which immune cells cross the blood-brain barrier and attack myelin, the protective sheath that surrounds nerve fibers the way insulation surrounds an electrical wire. Myelin allows nerve signals to travel quickly and efficiently along their pathways. When it is damaged, those signals slow, distort, or fail to arrive at their destinations. The result can be a spectrum of symptoms: blurred vision, numbness, difficulty with coordination and balance, fatigue, cognitive changes that vary from person to person and from episode to episode, depending on which nerves have been affected. Multiple sclerosis affects approximately 1 million people in the United States, and research continues to move toward understanding what triggers the immune system's crossing of the blood-brain barrier and how to gently redirect it. Lupus, systemic lupus erythematosus, is perhaps the most wide-ranging of the autoimmune diseases, a condition in which the immune system produces antibodies against the body's own DNA and cellular components, triggering inflammation in an unpredictable variety of organs. The skin, where it may produce a characteristic butterfly rash across the cheeks and nose. The joints, where it causes pain and swelling. The kidneys, where it may lead to serious damage. The heart and lungs, and sometimes the brain. Lupus follows a pattern of flares and remissions, periods of active inflammation alternating with periods of relative calm, making it difficult to predict and deeply disruptive to live with. It affects women predominantly and disproportionately affects women of color. It is, in its nature, a reminder that the immune system touches every part of the body, and so, in its misdirection, it can reach every part as well. Genetics plays a real and meaningful role in autoimmune disease. Certain gene variants, particularly those involved in immune regulation and self-recognition, increase a person's susceptibility to developing an autoimmune condition. But genetics accounts for only approximately 30% of the overall risk. The remaining 70% is shaped by factors outside the genome. The microbiome, which calibrates the immune system from its earliest days. Environmental exposures, including certain infections, chemicals, and ultraviolet light. Chronic stress, which alters the landscape of immune activity over time. And perhaps a long list of other influences that research is still in the process of identifying. This means that for most people, the development of an autoimmune disease is not destiny. It is a convergence of genetic tendency and environment, of timing and circumstance, of the body and the world it moves through. An allergy is, at its core, a case of mistaken identity. The immune system identifying a substance that poses no actual threat to the body and mounting against it a response as urgent and elaborate as the one it reserves for genuine pathogens. Pollen, which is simply a plant's way of carrying genetic material from flower to flower. Peanut protein, a component of a perfectly ordinary food. The shed skin cells of a cat, drifting through the air of a sunlit room. These things are harmless, and yet in the body of a person with an allergy, they are met with alarm, with histamine release, with inflammation, with the full dramatic apparatus of an immune system convinced that it has encountered something dangerous. The immune system is not wrong to respond with such dedication, it is simply responding to the wrong thing with the right intensity at the wrong time. At the center of most allergic reactions is a class of antibody called immunoglobulin E, or IgE, a molecule whose evolutionary purpose was likely the defense against parasites, but which in modern parasite-scarce environments sometimes turns its attention toward harmless allergens instead. When a person is first exposed to an allergen, say pollen or a specific food protein, and the immune system makes the decision for reasons that are not fully understood to treat it as a threat, it produces IgE antibodies specifically shaped to recognize that allergen. These IgE molecules attach to the surfaces of mast cells, immune cells stationed throughout the body's tissues, and wait. When the allergen is encountered again, it binds to the waiting IgE, and the mast cell responds by releasing histamine and other inflammatory mediators, producing the symptoms we recognize as allergic reaction: the sneezing, the swelling, the itching, the tears. Anaphylaxis is what happens when an allergic response does not stay in one place, when it becomes systemic, flooding the entire body in a wave of immune activation that can, within seconds or minutes of allergen exposure, become life-threatening. Blood vessels dilate so suddenly and so completely that blood pressure drops precipitously. Airways narrow as the smooth muscle around them contracts. The throat may swell. The heart races. The the person may lose consciousness. Anaphylaxis is the immune system's most dramatic overreaction, and it requires immediate treatment with epinephrine, a medication that works by narrowing the blood vessels and opening the airways, counteracting the very signals the immune system has released. Without treatment, anaphylaxis can be fatal within minutes. With treatment, the body returns to its ordinary equilibrium, shaken but intact, the immune system's alarm finally quieting. Food allergies affect approximately 32 million people in the United States, and the number has risen significantly over the past few decades, a trend that researchers are still working to fully understand, though the microbiome, dietary changes, and reduced early life microbial exposure are among the factors under investigation. Peanut allergy is among the most common and most serious. It affects approximately 2% of the American population and is one of the most frequent causes of fatal and near-fatal anaphylactic reactions. It tends to be lifelong, unlike some food allergies that children outgrow, and it requires a level of daily vigilance that shapes meals, travel, social gatherings, and schools. For those who live with serious food allergies, the ordinary world contains a geography of invisible risks that others rarely think to notice. There is a pattern in allergic disease that researchers call the atopic march, the tendency for allergic conditions to appear in a sequence across childhood, with one condition seeming to clear the path for the next. Eczema often appears first, in infancy, as the immune system of the skin begins to overreact to environmental contact. Allergic asthma and food allergies may follow in toddlerhood. By school age, hay fever, allergic rhinitis, often emerges as a new manifestation of the same underlying immune sensitivity. Not every child follows this sequence exactly, and not every child with one atopic condition develops the others. But the pattern is consistent enough to suggest that these conditions are not separate illnesses so much as different expressions of the same fundamental tendency. A shared signature of an immune system that is, in a specific and consistent way, set just slightly too high. One of the most significant shifts in the scientific understanding of food allergy in recent years has come from clinical research suggesting that early introduction of potential allergens, rather than avoidance, may actually reduce the risk of developing an allergy. The LEAP trial, published in 2015, found that infants at high risk for peanut allergy who were regularly given peanut-containing foods from early infancy had an 80% lower rate of peanut allergy by age 5 compared to infants who avoided peanuts. This finding reversed decades of clinical guidance and opened a new understanding that the immune system in early life may need exposure to potential allergens in order to learn to tolerate them. That tolerance, like immunity, is something the body builds through encounter and practice, not through the avoidance of the thing it needs to learn to welcome. The placebo effect, the measurable improvement in symptoms that can occur when a person believes they are receiving effective treatment, even when they are not, has been documented in allergy research in ways that illuminate something profound about the relationship between the mind and the immune system. In studies of allergic patients, placebo treatments have produced measurable reductions in immune markers, reductions in histamine release, and subjective improvements in symptoms. The brain, through its connections to the immune system via the autonomic nervous system and through its influence on cortisol and other hormones, can genuinely modulate the intensity of an immune response, not by wishing, but through real and measurable biological pathways. The immune system is not separate from the mind that inhabits the same body. It listens to what the mind says, and sometimes it answers. Sleep is not rest from the immune system's perspective. It is the immune system's most productive and restorative period. During deep sleep, the body releases a surge of cytokines, specifically the ones that promote healing, fight infection, and consolidate the immune memory formed during the day's encounters. Growth hormone, released in abundance during deep sleep, supports tissue repair throughout the body. The lymphatic system, which does not have its own pump the way the cardiovascular system has the heart, relies in part on the body's movement and breathing to circulate lymph. And during sleep, a newly discovered system in the brain called the glymphatic system activates, flushing metabolic waste from neural tissue in a cleansing that can only happen when the mind is quiet and the body is still. Sleep is not the absence of biological activity. It is the body's most intensive maintenance shift, and the immune system is its most dedicated night worker. The relationship between sleep deprivation and immune function is not subtle. In a study published in the Journal of Experimental Medicine, researchers found that losing even a single night of sleep could reduce the activity of natural killer cells, the immune system's continuous cancer and virus surveillance patrol, by up to 70%. 70% in a single night. The natural killer cells did not disappear from the blood. Their numbers remained relatively stable. But their activity, their capacity to actually identify and destroy the cells they were designed to eliminate, dropped precipitously. The study found that this effect reversed after recovery sleep, which is reassuring. But it underscores something important. Sleep is not optional maintenance for the immune system. It is the environment in which the immune system does its most irreplaceable work. Cortisol, the hormone produced by the adrenal glands in response to stress, is, in acute situations, an immune ally. In the immediate moments of a perceived threat, cortisol helps mobilize energy, sharpen attention, and actually prepare the immune system for potential physical injury. But cortisol is designed for acute stress, not chronic stress, for the sprint, not the marathon. When stress becomes prolonged and cortisol levels remain chronically elevated, the immune system begins to suffer. Cortisol suppresses the production of lymphocytes, reduces the sensitivity of immune cells to signaling molecules, and impairs the inflammatory response in ways that leave the body less able to respond effectively to infection. Chronic stress does not break the immune system abruptly. It wears at it slowly, quietly, the way wind wears at stone, patiently, continuously, in a way that is not dramatic until it suddenly is. Among the most striking demonstrations of the immune-stress connection is the well-documented phenomenon of viral reactivation under psychological stress. Many people carry dormant viruses in their bodies. The herpes simplex virus responsible for cold sores, the varicella zoster virus that caused childhood chickenpox and can resurface decades later as shingles, viruses that the immune system has contained but not eliminated, keeping them suppressed in a state of quiet latency. Psychological stress, the anticipation of an exam, a period of grief, a season of sustained workplace pressure, has been shown in peer-reviewed research to reactivate these latent viruses, tipping the balance between the immune system's suppression and the virus's attempt to replicate. The stress does not create the virus, it simply shifts the equilibrium, very slightly, in a direction the virus was always waiting for. Loneliness is not merely an emotional experience. It is a biological condition with measurable consequences for immune function. Studies examining the immune profiles of chronically lonely individuals have found elevated inflammatory markers, reduced natural killer cell activity, and altered gene expression in immune cells, consistent with a state of heightened threat alert and reduced antiviral defense. Some researchers have described the immune effects of chronic loneliness as comparable in magnitude to the effects of smoking 15 cigarettes a day. A comparison that, whatever its precise accuracy, underscores that social connection is not a comfort but a biological necessity, a condition the body has evolved to require with the same seriousness that it requires food and sleep and warmth. We are, in our cells as much as in our hearts, creatures made for each other. Laughter is one of the body's gentlest and most available medicines, and it has real, if modest, effects on the immune system. Research has shown that laughter triggers the release of endorphins, the body's internal opioid-like compounds, which reduce the perception of pain and create a brief but genuine sense of well-being. It also reduces cortisol and adrenaline, the stress hormones that chronically suppress immune activity. Some studies have found increases in natural killer cell activity and immunoglobulin levels following laughter interventions. The effects are real, though not dramatic. Laughter is not a treatment for serious illness, but it is a genuine contribution to the immune system's resilience, a form of biological care that costs nothing, requires no prescription, and has been practiced by human beings since long before anyone thought to study it in a laboratory. Moderate exercise, the kind that elevates the heart rate and quickens the breath without pushing the body into exhaustion, is one of the most reliably beneficial things a person can do for their immune system. During and after aerobic exercise, the circulation of immune cells through the blood increases significantly. Natural killer cells, T cells, and neutrophils are mobilized from their reservoirs in the spleen and bone marrow, sent out into circulation at higher concentrations, increasing the immune system's capacity to detect and respond to threats. Regular moderate exercise has also been associated with reduced levels of inflammatory markers, with better vaccine response, and with a lower risk of certain cancers, benefits that accumulate over time, each workout contributing to a baseline of immune resilience that grows quietly and incrementally across a lifetime of movement. Exercise is one of the most powerful things a person can do for immune health. But like most powerful things, it has a threshold beyond which its effects reverse. Intense, prolonged exercise without adequate recovery, the kind experienced by endurance athletes in the days following a marathon or a high-volume training block, temporarily suppresses the immune system, creating what researchers call the open window of increased susceptibility to infection. Natural killer cell activity decreases. IgA concentrations in saliva and mucous membranes drop. The body, having devoted enormous resources to the physical effort of extreme exercise, has temporarily less to spend on immune surveillance. This is not an argument against exercise. It is an argument for the thing that all biological systems require to sustain their function: rest, recovery, and the restoration that comes only from giving the body time to rebuild what it has spent. Mindfulness meditation, the practice of sustained, non-judgmental attention to the present moment, often anchored to the breath, has been the subject of a growing body of clinical research examining its effects on the immune system, and the findings are consistently, if modestly, encouraging. Regular mindfulness practice has been shown to reduce inflammatory markers in the blood, including C-reactive protein and interleukin-6, both associated with chronic low-level inflammation. It has been shown to improve immune response to vaccines, to reduce the rate of viral reactivation in people carrying dormant herpes viruses, and to reduce the activity of genes involved in inflammatory signaling. The mechanism appears to involve the reduction of stress-related cortisol, the restoration of parasympathetic nervous system balance, and perhaps a direct influence of the brain's changed state on immune cell behavior. Stillness, it turns out, is a form of action. The immune system's capacity to distinguish between self, the body's own cells, proteins, and molecules, and not self, everything that does not belong, operates at a level of molecular precision that surpasses anything human technology has yet produced. Every cell in the body displays on its surface a set of molecules called the Major Histocompatibility Complex, or MHC, which acts as a kind of identity badge, a molecular declaration of belonging. Immune cells read these badges continuously as they patrol the body, recognizing the self-markers of healthy cells and passing them by, flagging anything that displays a different or absent signature. This recognition system is so precise that it can detect a single altered protein on the surface of a cell, a cancer cell just beginning its departure from normal, and mount a response against it. It is a system of recognition more nuanced than any passport, any fingerprint, any face. For decades, there was a popular belief that sharks do not get cancer, a myth that arose partly from their ancient evolutionary lineage and partly from early observations of their unusually robust health. The reality is more nuanced and, in its own way, equally interesting. Tumors have been documented in multiple shark species, and sharks are not cancer immune. But they do possess immune adaptations that are genuinely remarkable and scientifically significant. Sharks have circulating immune compounds called squalamine with broad-spectrum antimicrobial properties. Their antibodies include a novel type called IgNAR, single-domain antibodies, far smaller than conventional antibodies, that can reach molecular targets inaccessible to standard antibodies. Shark immune systems are being studied not because sharks are immune to all disease, but because what they have evolved over 400 million years may teach us something important about what immunity can be when shaped by deep time. The thymus, the small butterfly-shaped gland that sits just above the heart and beneath the breastbone, is among the most active and important organs of childhood. It is here that T cells complete their education, tested, selected, and released only when they have demonstrated the ability to recognize self from not self without attacking either. During childhood and adolescence, the thymus is large and busy, processing enormous numbers of T cells in preparation for a lifetime of immune defense. But after puberty, it begins a slow process called involution. The thymic tissue is gradually replaced by fat and connective tissue, and by middle age, only a small remnant of active thymic tissue remains. The T cells it produced in youth persist and continue to work, But the thymus's great period of production is behind it, a gland that gives the most it will ever give in the first years of a life. By the time a baby is born, it has already been building an immune system for months. T cells first appear in the developing fetus as early as 14 weeks of gestation, 12 weeks before the end of the first trimester is complete, emerging from the fetal liver and thymus in a developmental sequence that mirrors, in miniature and at speed, the evolutionary history of the immune system itself. By the second trimester, a basic immune architecture is in place. Innate immune cells circulating through fetal blood, lymphoid organs beginning to organize, the first B cells appearing in the bone marrow. The adaptive immune system is less mature at birth, but it is not absent. It is a system still finishing its training, still waiting for the world to give it the education that only experience can provide. The immune system does not begin at birth. Birth is simply when it meets the world it was made to protect. The placenta, that extraordinary temporary organ that grows at the interface between a mother's body and the body of the child she carries, performs one of the immune system's most delicate negotiations. On one side of its layers of cells is the mother's blood, carrying her immune cells and her antibodies. On the other side is the fetus, genetically distinct from the mother, bearing paternal antigens that the mother's immune system might, in other circumstances, identify as foreign and attack. The placenta allows certain maternal antibodies, particularly immunoglobulin G or IgG, to cross from the mother's circulation into the fetal bloodstream, providing the newborn with a gift of passive immunity for the first months of life outside the womb. But it carefully prevents the passage of full maternal immune cells, which could cause a graft versus host type reaction in the fetal tissues. It is a border so precise, so intelligent in its selectivity that it may be the most sophisticated filter in the natural world. In the connective tissues of the skin, the lungs, the gut, the lining of blood vessels, scattered throughout the body's vast interior landscape, there live cells called mast cells, and they are among the most patient things in biology. A mast cell may inhabit a tissue for years, even decades, without ever being activated. It simply waits, coated in IgE antibodies primed with granules of histamine and other inflammatory mediators. It waits for the signal, the arrival of an allergen or a pathogen that matches its surface-bound antibodies, that will tell it the moment has come. Most mast cells wait their entire lives for a signal that never comes, and they tend their tissue peacefully, contributing to local immune surveillance, never firing the alarm they were made to carry. There is something quietly beautiful about this, a cell that lives its whole life prepared for an emergency that, in the kindest version of events, never arrives. The immune system, like nearly every biological system in the body, follows a circadian rhythm, a roughly 24-hour cycle of activity and relative rest that is synchronized to the body's internal clock and to the external cues of light and darkness. Certain immune functions peak during the night and the early hours of morning. Natural killer cell activity, the production of certain cytokines, the proliferation of immune cells in the lymph nodes. This is one reason why illness, the subjective experience of symptoms, often feels more acute after dark. The immune system's nighttime activity is, in part, what produces the fever, the fatigue, the aching heaviness of an infection being actively fought. The immune system does not rest at night. It works harder. And the body's nighttime retreat into sleep is, in this light, not an abandonment, but a collaboration. The conscious mind stepping aside so that the immune system can do its deepest work. During pregnancy, a small number of the mother's cells cross the placenta and enter the fetus, and some of these cells survive in the child's body not just for months or years, but for decades, sometimes for the rest of the child's life. This phenomenon is called microchimerism, from the Greek chimera, the mythological creature made of parts of different animals, and it means that many adults carry, quietly embedded in their tissues, a small population of cells that originally belonged to their mothers. Researchers have found maternal cells in the hearts, livers, spleens, and brains of adult children. What these cells do, whether they contribute to immune function, whether they cause harm, whether they simply persist as living traces of a biological intimacy that birth does not fully end, is still being investigated. But their presence is remarkable. A mother's body, in a very literal sense, never entirely leaves her child. The immune system's reach extends even into the architecture of the mind. In the brain, a specialized population of immune cells called microglia, which account for roughly 10% of all cells in the central nervous system, perform functions that go far beyond simple immune surveillance. During early brain development, microglia are actively involved in the process of synaptic pruning, the careful elimination of unnecessary or underused neural connections, a sculpting process that is essential for the brain to mature from the densely connected sprawl of infancy into the more efficient and specialized networks of childhood and adulthood. Microglia identify synapses marked for removal, tagged by complement proteins, components of the innate immune system, and consume them. The brain you have now is partly the result of this immunological editing, the immune system reaching into your earliest neurology, shaping who you became. One of the most elegant strategies that cancer cells employ for survival is the mimicry of the body's own self-signals, the molecular equivalent of wearing a disguise, displaying surface proteins that tell patrolling immune cells, "I belong here, I am not a threat, pass by and leave me in peace." For years, this disguise worked, and cancer cells could grow in the shadow of an immune system that had been deceived into tolerance. Cancer immunotherapy, one of the most significant advances in oncology of the past 2 decades, works by removing or disabling this disguise. Checkpoint inhibitors, a major class of immunotherapy drugs, block the proteins that cancer cells use to suppress immune recognition, lifting the veil and allowing the immune system to see the cancer for what it is. The treatment does not bring a new weapon to the body. It simply restores the immune system's ability to use the weapons it has always had. Among the most dramatic interventions in modern medicine is the bone marrow transplant, a procedure that, in certain cases of severe autoimmune disease, can offer something close to an immune system reset. In this procedure, the patient's existing immune cells are largely eliminated through chemotherapy or radiation, and new stem cells from a donor, or in some cases from the patient's own previously stored marrow, are infused into the bloodstream, where they migrate to the bone marrow and begin the process of building a new immune system from the ground up. For patients with diseases like multiple sclerosis or lupus that have proved resistant to other treatments, this procedure has produced remissions measured in years, even decades. It is one of the most profound demonstrations of the immune system's regenerative potential, the capacity to begin again, to rebuild from the most fundamental level, to start the long conversation of self-knowledge anew. Identical twins share the same DNA, the same genetic blueprint, the same code for every protein their bodies will ever make. And yet their immune systems, even in early life, begin to diverge, shaped by the different microbes they encounter, the different infections they experience, the different stresses and exposures that accumulate as 2 separate lives unfold along paths that, however similar, are never truly the same. Studies comparing the immune profiles of identical twins have found that by middle age, the 2 immune systems can differ substantially, more influenced by lived experience than by shared genetics. The immune system is, in this sense, the most biographical of the body's systems, a living record of where a person has been, what they have survived, what the world has brought to their door, and how they met it. Every pathogen your immune system has ever encountered and defeated has left something behind, not damage, not scar tissue, but memory. A memory B cell shaped to recognize the exact surface proteins of a virus you contracted as a child. A memory T cell carrying the molecular record of a bacterial infection you weathered without knowing its name. A subtle tilt in your antibody repertoire, a particular sensitivity in certain lymph nodes, a trace of every battle your immune system has ever won. You carry all of this with you, always, not as a burden but as a resource, a quiet accumulation of hard-won knowledge stored in the living tissue of your blood and lymph and bone. Your immune system is, in this sense, a kind of autobiography. Not the story of your thoughts or your choices, but the story of your body's encounters with the world, written in the only language the body knows. Right now, at this very moment, as your breathing has grown slower and your muscles have released their grip on the day, and the darkness has deepened around you into something soft and enveloping, your immune system is working, not in conflict, not in crisis, but in the gentle, continuous way it always works when the body is at peace, patrolling, monitoring, tending. Natural killer cells making their quiet rounds, memory cells holding their patient archive, cytokines carrying their soft chemical messages from tissue to tissue, maintaining the balance that allows everything else to function. Macrophages consuming the cellular debris of the day. B cells resting between activations, their memory intact, their readiness undimmed. It is always doing this, whether you are afraid or joyful, distracted or present, awake or in the deep country of sleep. Your immune system has never stopped caring for you, not for a single moment of your life. And tonight, as you drift toward rest, it is still here, still working, still holding you, gently, precisely, and without end. And so we come gently to rest at the end of this long, quiet journey through the world that lives inside you. 100 facts, 100 small windows into a universe so intricate and so devoted that it can only be understood as a form of love. The body's love for itself, expressed in 2 trillion cells and 1 trillion molecular keys and 75 years of faithful memory. You do not have to think about this world to be held by it. You do not have to understand it to be protected by it. It was here before your first thought, and it will tend to you long after your last thought tonight dissolves into sleep. So let it. Let the breath come and go on its own. Let the body do what the body knows. And let yourself fall slowly and completely into the safe and living dark that has always been waiting to catch you.